I'm Terry Klinker. In our last session, we solved graphically for our Flair Furniture project. In this session, I'm going to talk about different types of solutions that we could get. All right, there are 4 different types of solutions we could get. The first is called unique optimal solution. A unique optimal solution is exactly what it sounds like. It means that I have one combination of my decision variables that provides that maximum or minimum quantity. In our Flair Furniture process, we went through and found out we had our 4 corner points. We solved for them, and we found out that at 320, 360, we made $4,040. So we made $4,040 here. We made $3,000 here. We made $3,500 here, and of course we made $0 here. This was the optimal solution. There was only one combination in our feasible region that met that. That is a unique optimal solution. The second one I want to talk about is multiple optimal. It's possible that more than one combination of your decision variable values will give you the same maximum or minimum optimal solution. All right? In this case, what if instead of $4,040 here, what if I got $4,000 here? If I make 320, 360, I would make $4,000. And if I made 500 tables and no chairs, what if I also got $4,000? Now, yes, I know it's not true, but what if it was? That means that I could make this mixture and get $4,000, or I could make this mixture and get $4,000. That's a multiple optimal solution. I have more than one point that gives me the most profit. I now can decide whether I want to make a mixture of tables and chairs, or if I just want to make all tables. The other thing to remember is this straight line segment between these 2 points, if there is a straight line segment between it, every mixture of tables and chairs along this segment would give me $4,000 in a multiple optimal solution. Each combination on this line segment would give me $4,000 of profit. That is multiple optimal. The third one I want to talk to you about is called infeasible. An infeasible solution is just what it sounds like. There are no combination of variable values that meet all of the constraints. I can give you an example you might be familiar with. All right? The federal government is excellent at putting a whole bunch of constraints on things to the point where there's no way you can meet all of them. It's one of the best things they do. They'll sit there and they'll come up with a very good program, and then they'll say, well, we don't want it to go here, or we don't want it to go there, or we don't want it to do this. By the time they put all these constraints on, nobody qualifies for the money. You probably ran into some of this when you were trying to qualify for financial aid. They sit there and they pound their chests and say, look at all this money we put out for college financial aid, but then you go to do it and you find out that either your family makes just a little bit too much, or you're not taking the right program, or this is wrong, or that is wrong. And the first thing they do is tell you, you don't meet the requirements. That's an infeasible solution. In our case here, what if we said, okay, we've got these constraints here. What if I also add a constraint in here that says, all right, number of chairs must be greater than or equal to 1,000. So x1 must be greater than or equal to 1,000. In this case, I would come out here to x1 equals 1,000. It's going to be a vertical line so that x1 is always 1,000. And I've got to make more than 1,000, so I've got to be on this side of the line. Which combination of x1 and x2 meets all of these requirements and meets this requirement? And the answer is none. There are no solutions that meet all of that. That would make it infeasible. When you have a constraint, anytime you add a constraint to your system, when you're trying to do a program, when you're trying to do a project as you move out into the business world, Every time you add a restriction onto something, it makes it harder to do. As I add constraints onto this, my optimal solution here was $4,040. Every time I add a constraint, I will either make $4,040 or less. I can never get better with more constraints. I can get worse, I can get infeasible, but I can't get better. So always think about, does that constraint need to be there? The last one I want to talk about, and it's one that throws people off more than any other, is called unbounded. An unbounded solution is one where there's no limit. You can't have an optimal solution. You can't find a maximum or a minimum because there is no maximum or minimum. As one of your variables proceeds to infinity, you become more optimal. So how would this work? Well, let me give you an example on this one. What if I wanted to maximize the quantity x1 plus x2? And that would be subject to, ST is subject to, the following constraints. Okay, so I've got a constraint that x1 must be less than or equal to 8, and 2x1 plus 4x2 must be greater than or equal to 4. Well, first thing we need to do is, of course, graph things. So we'll put our graph here. Here's x1. Here's x2. We know we must have non-negativity, so we have to be on this side of, we have to be in quadrant 1. Our first constraint is x1 must be less than or equal to 8. All right, I'll come out here to 8. I have a vertical line, and I must be on this side of x1 equals 8. The second one is 2x1 plus 4x2 equals 4. Well, I need 2 points on this line. All right? So let's go through x1, x2. If x1 is 0, x2 must equal what? Well, x2 must equal 2. If x2 equals 0, x2 must equal 1. 2 times 0 plus 4 times 1 equals 4. If x2 equals 0, x1 must equal 2. Got my 2 points on the line. I come out here to 0, 1, 2, 0. Put my line through it. What side do I need to be on? Well, the origin isn't on this line. Let's test it. 0 plus 0 is not greater than or equal to 4. So I want to be on the non-origin side of the line. This is now my feasible region. My corner points are here, here, and here. So I go through and test things. Got my corner points and my objective function value. Corner point is at 0, 1, 2, 0, and 8, 0. x1 plus x2 is 0 plus 1 is 1. 2 plus 0 is 2. 8 plus 0 equals 8. I'm trying to maximize, so it would be 8. Except, notice there's no lid. There's no lid here. I can keep going this way. When you see you have no lid on it, you need to test another point. Let's test a point out here at x2 equals 10 and x1 equals 8. So we'll test this point. At 8, 10, I end up with 8 plus 10, which is 18. What if I go up here to 1,000? At 8, 1,000, 8 plus 1,000 equals 1,008. As I keep going up, as x2 keeps going towards infinity, I get to be more optimal. It's unbounded. That's an unbounded solution. Unbounded solutions can be tricky. What if instead of maximizing it, you can't just look at it and say there's no lid on it, therefore it's unbounded. What if instead of maximizing, I want to minimize this quantity? Well, if I want to minimize that quantity, as it goes up, it keeps getting bigger. The minimum one I have here would be 0, 1. Therefore, it would have a feasible solution. It would be at 0, 1. What if I continue to want to maximize, but instead of plus 1, this is a plus x2, it is a minus x2. Now these quantities change. This becomes minus 1, minus 0, minus 0, minus 10, minus 1,000. 0 minus 1 is minus 1, 2, 8, minus 2, minus 992. Since I'm trying to maximize, this would be the biggest number. So just because there's no lid doesn't mean that it's unbounded. You have to test it at the corner points and then at some points as your unconstrained variable goes towards infinity.